In this video, we're going to talk about the probability of two events both happening. In more mathematical terms, we call that the probability of the intersection of the two events. Those two sentences just mean the exact same thing. The probability of two events both happening, in other words, the probability of the intersection of the two events. It's the same thing, just said different ways. So there's two sort of options for what can happen when you want two things to happen. And so let's look at the first of those, all independent events. Independent events are events where the outcome of one event does not affect the outcome of the other event. The formula for finding the probability of two events, A and B, both happening, is equal to the probability of event A happening times the probability of event B happening separately. One important thing to notice is that we use this notation with the P and then in parentheses something. So here we have on the left side P and then A and B in the parentheses, and then on the right side of the equal sign we have P and then in parentheses A times P in parentheses B. It's important that we know that this does not mean, the parentheses here do not mean multiplication. This means the probability, the P stands for probability, of whatever's in the parentheses. So the probability of A and B both happening. And means they both happen. And then over here, this equals P, the probability of A happening, times P, the probability of B happening here. Okay, easy mistake to make and think that means multiplication, but it does not. This symbol here, that is multiplication, but the parentheses here do not mean multiplication. Let's look at a quick example here of an independent event. So our example says we have two standard six-sided dice, and we roll them. We want to know what's the probability of rolling a 2 and a 3. Six-sided dice, dice is two of them, one is a die. On each die you have one face with one dot, one face with two dots, one with three dots, four dots, five dots, six dots. Standard to talk about dice with probability, because you have an equal chance of landing on any one side. So using our notation from up above, I can rewrite this same statement, the same question as saying, okay, what is the probability of a 2 and a 3? Now, because these are independent events, this should just equal the probability of rolling a 2 times the probability of rolling a 3. Now, first of all, why are these events independent? Well, again, our definition of independent says that the outcome of one event does not affect the outcome of the other. When you roll your dice, the number that shows up on the first die has no effect on what number shows up on the second die. They're totally separate things. They're just happening together. So we need to know what's the probability of getting a 2, and then what's the probability of getting a 3, and then we can multiply those things together. Well, because we have 6 sides, and only one of them is 2, I have a 1 in 6 chance of getting a 2. The actual number that I want doesn't really matter. It's just that there's only one number that I want out of the six total possible numbers I could get. So same for the 3. There is only one 3 that I could get out of the 6 total possible number of things I could get. So the probability that I will get both a 2 and a 3, for whatever reason I need those things, that's what I want here, it's going to be 1 over 6 times 1 over 6, or 1/36. Now for probability, sometimes you like to leave your probability as a fraction, sort of saying I have a 1 in 36 chance of getting a 2 and a 3, or I could say, I could convert this into a decimal, which that as a decimal is 0.27, and the 7 repeats. We put the bar over it to show that that 7 just keeps going on literally forever. Sometimes we also like to write our probabilities as a percentage. So to turn a decimal into a percent, you move the decimal point 2 places. So this would be 27.7%. And again, this 7 just keeps on going. So if your events are independent, they do not affect each other, you just multiply the two things together. We should point out here real quick that this is for rolling a 2 on the first die and a 3 on the second die. I want it in this specific order. 2 on the first, 3 on the second. It does matter that I want it in this specific order. All right. Now we've looked at independent events. We also, of course, events. Now, dependent events, like you might assume, are events where the outcome of one event does affect the outcome of the other event. Independent, they don't affect each other. Dependent, they do affect each other. But the formula looks very similar. Still on the left side, I want the probability of A and B, and being the key word here. I want both of them to happen. And that's still going to equal the probability of A times the probability of B, but this time we have to adjust and say it's not just the probability of B, but it's the probability of B following A. So once A has already happened, what's the probability that B will happen now? So in this example, instead of looking at dice, we're going to look at cards. So the example says that 2 cards are drawn from a standard deck of 52 cards. What is the probability of drawing a king and a queen? Well, I know that from this formula, really, I can rewrite this as the probability that I get a king, and I'm going to abbreviate my and with a nice ampersand there, king and queen. Now my formula says that I'm just going to take the probability of getting a king as it already is. So the probability of getting a king is 4 out of 52. There are 52 total cards I could get. 4 of them are kings. The king of hearts, diamonds, spades, and clubs. Now I also then want to, with my second draw, get a queen. So I need to look at the probability that I get a queen. Now initially you might think, well, there's 52 cards, there's 4 queens, so it's the same. But I've already drawn 1 card. So that means there's 51 cards remaining. There's still 4 queens because we're saying I've already drawn one card and it's a king. What's the probability that that second card is a queen? So I haven't drawn any queens yet. So there's still 4 queens remaining, but there are now only 51 total cards remaining. And that's why this is an example of dependent. Because once I draw that first card, that does affect the outcome of my draw for the second card. It's not a big difference. It just turned this denominator from a 52 to a 51, but it did change it. It affected it in some way. So that's why drawing 2 cards is an example of a dependent event. But now I just need to actually multiply this out. I'm going to simplify before I multiply. 4 over 52 can be simplified to be 1 over 13. 4 over 51 cannot be simplified at all. So now I'll multiply straight across, and I'll get 4 over 663. That's a bad 3. That's a little better. So that's my fraction, and again, for probability, I either write it as a fraction, a decimal, or a percentage. This is a very small decimal, 0.00603. I've rounded a little bit there. And then if I turn that into a percentage, move the decimal point 2 places to the right, and we'll get 0.603%. So if you want two things both to happen, which we call the intersection of the two events, you need to first decide, okay, are these dependent or are these independent events? If they're independent, you just multiply the regular probability of each event. If they're dependent, you multiply the probability of the first one happening times the new modified probability of the second one after the first one already happened. One key thing to notice here as well, though, is that for both of these types of events, dependent or independent, both of them we're looking for A and B, and we end up multiplying on the right side. In another video, we'll explore what happens when you look for A or B, and we'll end up adding instead of multiplying. So something to keep in mind for the future is that when I want the intersection A and B, I multiply. When I want the union A or B, I add. And once again, there can be a small twist in there, but we'll look at that in another video. Okay, so that's probability of two events both happening, or what we call the intersection of two events.